So one of you guys asked a very interesting question, and I thought I'll make this lecture just to address that particular question in details. Let's jump into it. So this comes from Adam Salama. Hopefully that's how you pronounce it. There's an H in your name, so I suppose it's Adam. So the question is, explain analyze shows bitmap scan instead of an index only scan. Why is that? And thank you, by the way, Adam, for actually including the script, because I built this lecture maybe months ago, even maybe years, right? So I have no idea. If I read a question, I don't remember anything. So by you actually providing exactly what you did, I just copy it in my Postgres instance, and I am with you exactly the same thing. And instead of asking me, oh, in this minute you did this, I have to open the lecture, go to the minute, it takes time, right? This way, I just look at what you have. I'm in the same boat as you. So thank you for doing this. This is awesome if you do this, right? So what Adam is experiencing is he created the grade table. He created the partitions. He just slammed a bunch of rows, 1,000 rows, and then immediately did a query on the main partition, doing explain, analyze, select, count star from grades part where G is equal 1. So he wants the first grade. That we know that since G is equal 1, we're going to hit the first partition, right? Between 0 and 35, because that's the range, right? So that's how it works. So we're going to hit that. And we have an index there because we create an index on the main. An index will be created on each partition, because a partition is really just a table, right? Each one is just an individual table. And this partition, this main part, is really just a logical thing, a nice view for you, So what Adam I suppose the question is, like, they got a bitmap index scan, right? On the G035G index, which is perfect. That's the index of that table, right? And the cost here is 0 to 4. And again, I made a mistake in one of my lectures that says, oh, this is millisecond. That's not correct. It's just a unit that Postgres uses. And this unit means it's a cost, right? The more the value, the higher the cost. You can think of it as I/O, you can think of it as milliseconds, not really, but it could be anything. And that's just the value, that the higher the cost, the worse the performance, right? So we estimated 9 rows. We got 9 rows with this, so it's just an estimate, and then the actual gave us 5. But the question is, like, why is it not using the index only scan? It's a count, right? So I'm just counting the rows. Like, why does it have to go to the heap? And the cost of going to the heap is high, right? Because now going to the heap, you need to fetch the pages and all the columns for that table. Okay? So if you have like 100 columns, going to the heap will by default fetch the page and fetch the table, the tuple, right? And the table will by default give you all the columns, right? And I know some of you ask a question like, oh, in this case, like, why do we do select column? Just always do select star. No, not quite. While true, when you do a tuple query, you get all the column, but the parser still have to do work to actually crack that index and actually find the attributes that you're looking for by parsing the binary page in Postgres. So there is work there. It's not like free. So that's the first work. Then you have to serialize it to the data structure in Postgres. Then you have to transfer it to the client. So select star is bad regardless, even if it's a raw store, right? There is so much work, right? Especially like, let's say you have blob field, you're doing select star, you're pulling it from the toast table and then pulling it back to the network, to the client. Nah. All right, so back to the original question. Why did it do a heap scan, an index heap scan? And we talked about that, a bitmap index scan. What it does is it scans the index, and it doesn't really care about the columns per se, the tuples. It just make marks of the pages. Oh, we found page 0 and page 17 and page 30, right? These are the pages that contains the rows we want. That's all what it does, right? And then it takes that and fetches page 0 with all its tuples, fetches page, what did we say, 7, and then fetches page 31 with all the rows. And then it does an additional filter on the heap to filter out what it doesn't want. In this case, we're looking for grade equal 1, right? This is, in this case, the bitmap is doing it this way because it had to go to the heap for some reason. We don't know why in here. I know, I'm going to tell you why, right? But if it has to go to the heap, it doesn't use an index-only scan because it's not an index-only scan. We have to go to the heap to fetch an additional column. But what is the column that it needed? We didn't need anything. The answer is there are 2 hidden system columns that Postgres uses to maintain the MVCC, the multi-version concurrency control. And those are the Xmin and then Xmax and then some other columns. This lives as just another column in the table, in the heap, right? So in the pages, and there's just 2 additional attributes, including the tuple ID as well, right? So now, if you think about it, these 2 columns will tell you whether the row is visible or not, whether the tuple is visible or not. What does that mean? So if I am transaction, right? If I'm transaction 1 and I started, I'm doing some work here. I started. And meanwhile, after a little bit of while, I didn't commit. Transaction 1 is still running. And then another transaction continues to run, right? I started another transaction and inserted a bunch of tuples, right? And didn't commit. Does this transaction 1, should it see these rows? No, it should not, right? Because it started before that transaction. And even if it did, if transaction 2 did commit those rows, if I'm in transaction 1 and I started a query, I started running a long query, let's say I'm selecting everything, and just right after I started executing the query, then it's running, the other transaction committed the inserted rows. This transaction should not see those inserted rows because it started right before the commit, because that's how read committed works, right? Read committed works the moment at the start of the query, right? So yeah, once we finish that query, the next select will see those inserts. So that's how isolation works. We talked about it in details in this course, right? The problem here is Postgres does not trust the index, because the index has what? It has the key, which is the grades in this case. That's where we're building the B3 on. And the value that is corresponding to the key is the tuple ID, right? Which is basically the page index, which is 0, 1, which page, and which index in that page belongs to which tuple, right? So that's how the tuple ID works in Postgres. So that's the only information we have. So we have no idea that someone inserted something. When you insert something, you update the index as well, right? So when you read it, that transaction should check, am I supposed to see that row? Is this row deleted and I still need it? Is this row inserted and I'm not really need to see it? So this visibility information lives in the heap, in the table, as just another column, which is Xmin and Xmax. Xmin tells you that this is the transaction that started that created those tuples. Xmax tells you this is the transaction that killed the tuple or deleted it or even updated it, right? Because Postgres creates a new tuple for every update. So now, based on this information, Postgres said, all right, for Adam's queries, a select count, I know, I got this, but guess what? These are new stuff. He just inserted them, remember? They just inserted this row, and then immediately after that, he did the query. So based on Postgres, we'll say, well, I can't really trust those rows because they might not be visible for me. So I need to go to the heap to read the Xmin. And when I read the Xmin, I say, oh, this is a transaction that started before me and committed. I am supposed to see those rows. I am actually supposed to see them. So they will pull it back. Yeah. But you might say, ask the question now, does that mean that every query now has to go to the heap to check if it's visible? No, not really. Postgres has this optimization called the visibility page. Each page, there's like a data structure in memory that Postgres maintains that says, okay, page 0, don't bother going to the heap. All the rows in this page 0 are visible to every single transaction, right? There is no transaction that is running for a long time that requires the old version, or it requires not to see these rows for some reason, for isolation purposes. All of them are required. How do we do that? We do a vacuum on the table. If you do a vacuum on the table, Postgres will go through all of them and do this expensive check, which is like, is there anybody really running right now is there anybody running? Is there any transaction that is running that needs not to see this row? Like, is this one of these rows are invisible to any of them? The question is no, because nobody is running. So by running vacuum, right, I actually tested it. If you run vacuum right after this, and then you run experimentalize, you get an index-only scan. So that explains why do we get an index-only scan. And apply this to everything, right? Everything you get these heap, I think, yeah, the heap plan. There's like the heap fetches. You're going to see the heap fetches somewhere here. Sometimes I see it. I can't see it right now. But you see the number of heap fetches that we had to go to the heap for this, right? So that's basically one reason why in this case the plan completely is different. They say, hey, you know what? This is a brand new thing. I really need to go to the heap anyway, right, to do this. Well, that's one reason. Sometimes the index-only scan, in this case, will always do that. But again, it's always not guaranteed, right? Because especially in the count case, like you inserted a row, something is not visible, everything just falls apart. So it's really hard for the planner to pick up the right plan based on this information, right? So yeah, that's what I want to talk about here. It's really interesting to understand that. And based on that, you can explain some of the things that happen to you. I can't think of every possible situation, but always happen that if a planner does something, it does it for a reason. It might be a bad plan, right? Listen to me. It might be a bad plan because just the statistics are not up to date, or the statistics are not really smart enough for a specific use case. And that's basically another talk altogether. This is advanced statistics, right, and database. All right, guys, that's it for me today. Hope you enjoyed this lecture. Hey guys, one of you asked me a question about the cost unit in the Postgres plan here. I made a mistake in the lecture and I incorrectly referred to it as a millisecond, which is incorrect, right? And I want to correct that. So let's discuss that a little bit. All right, so this comes from Jasic. I'm sorry if I mispronounce your name. But the question is, like, in the video, you said that the cost unit is millisecond, but that's not true. He's right. According to Postgres, the unit is not in millisecond. It's just a unit defined by the database, right? And that's very critical, and I can agree with him, because that I just made a mistake. I think I was thinking that it's a millisecond. It has nothing to do with a millisecond. It's just a cost. It's just a number. And so when we look at a plan, and it's a good example to go through another question here that Adam actually posted, where these costs are actually just values, right? And you might say, if it's not millisecond, then what it is? Does it really matter? Right? You can think of it as I/O, like the cost of I/O, right? But it's a unit, right? What matters is the higher the value, the higher the cost of the query. That's all what matters, right? But it doesn't really equal to the number of milliseconds, right? So if I see a value like 4.2 here, doesn't mean that it's gonna take 4 milliseconds. No. That's all. And I corrected the lecture for that part. Yeah, it just says it's gonna cost me 4 units of whatever this costs. Maybe it's how many logical IOs I'm gonna do, how many CPU cycles is gonna take to process these things. So it's like a combination of things, and that is morphed into this unit. What we need to like is this is the first, as I said, like this is the cost to fetch the first row, this is the cost to fetch the last one, right? And that's what matters. But and the second part is like what it actually took me. So it took me way less, right? So that's part of the estimation versus the actual execution, right? If you see the estimation being way different than this, then we start looking at the statistics. Did we run vacuum or not, or did we, like, are we up to date? Is the statistics, or did we run analyze? Is everything is up to date or not? So this is actually very critical, and he actually posted a link here to an article explaining this a little bit more. So I apologize for the mistake if that confused you. But yeah, again, as I said, the cost here is a unit. Doesn't matter what it is. The higher value, the higher the cost. The lower the cost. The first entry is the cost to get to the first row. You will see that if you do an order by, that initial value is going to be high because just before the Postgres gives you an answer, it has to sort, right? And the cost to sort is added on top of everything, like the cost of the I/O, not only I/O, the cost of the I/O to fetch the page, the cost of the CPU, right, to calculate all this thing, and then it's added to the minimum value to get you that, right? All right, so to explain this, I wrote up two queries here, one with order by and one without order by. And I want you to notice this. The one without the order by, look at the cost. It's 0 because for each table, because I have partitions on this table, I'm doing select star from grades, right? So the cost to fetch the first row is 0. There is absolutely no cost because it's literally the first thing I'm going to do, right? So yeah, what's happening here is you can see the cost is 0 here because we're reading all the partitions, and then finally we're going to do an append, right? And return the first row. The cost to return the first row after reading all the partitions, probably not a good idea to do the partition because it's a little bit complex, but you guys get it, right? So the cost to get the first row off of all these partitions after we read all of them is 0. There's nothing, there's no cost because literally whatever the order that we got, just pick the first one, right? Which we have like a pointer to. So there's no cost to fetch the first one, right? The cost to get the last one is 21, right? But take this, with an order by on G, I said order by the grade. So here, again, if you notice that the cost to fetch the first rows here are 0. Why? Because we're not really technically ordering for each query on the partition. We're just reading it raw, right? But then after we appending all rows, the cost to append is nothing, right? To first fetch one, but the cost to append the last one that's the most cost. Then we apply the sort and look at that. The cost to give you the first row after the sort is 70. It's not 70 millisecond again. It's just 70 as a value here, right? So that's a higher value. That means, of course, 70 is greater than 0. And as a result, it's a lot, right? And the cost to give you the last after that is just 3 costs after that. So 73, right? So that's because we don't have much rows, but the cost to give you that. So be very careful when you're having order by, because that is the cost to give you the first row, especially if you have like if you give a query, the latency is here. Like what is the latency, especially if you're like fetching the first limit, like give me the first 1 row or 2 rows. Doesn't matter. If the planner has to do a query and has to sort, that cost has to be done first, then before the select, right? All right, guys, that's it for me today. Hope you enjoyed this lecture. I wanted to clarify that cost parameter and just hit it in the nail and correct my mistake. See you in the next one. Hey guys, some of you asked me a question about snapshot isolation, and why don't I mention it explicitly in the course compared to like the others, repeatable reads and the others. And the reason is like I come from a practical database usage, where these are not really spelled out differently. Like when we say repeatable read, mostly we really mean snapshot, right? Especially in Postgres, it's actually implemented the same thing, right? But it's just like the text box really overcomplicate things when it comes to explaining the difference between these. So let's actually sit down and truly think about the motivation behind repeatable read and snapshot, and clarify what is actually a snapshot, and try to answer this question in this lecture. Let's jump into it. So this comes from Baptiste. The question is, why you don't mention snapshot isolation level, Hussein? Like, why? You can mention everything except for a snapshot. The reason is really because like I have most experience with Postgres and MySQL and others, but snapshot itself is rarely you see it as an explicit platform as an isolation level. It's just there. It's implemented. Right? And sometimes it's even the default in some databases, right? And the difference really between the snapshot and repeatable read is really comes down to, I suppose, maybe the implementation. It really depends on the implementation, because if you implement isolation, you get repeatable read for free. So what the Postgres team actually implemented isolation, and they got repeatable read, and they didn't have an explicit repeatable snapshot isolation, right? So let's explain the difference. First, let's start with read committed, and I don't think we need this. Let's just talk through that. Yeah. So let's talk through read committed isolation level. Go through them all one by one. Let's finalize them one by one. Right? I start a transaction, right? And it's read committed. I start a transaction and it's read committed, right? And I do a select statement, right? Now, if I'm doing a select statement, the read committed should, by definition, start reading everything that was committed and visible at that moment of the query. Right? So if I square a query, anything that committed right before I started, I should see. That's the definition of read committed. So this, by definition, means that if I execute a query and I get 3 results, and then I execute another query and I get 5, that is fine, right? Because the next query, although it's the same query, was executed on another moment, on another timestamp, on another version. Think of it this way. This way, the version of the query is actually a query by query level in read committed. So that's why you get a different result every time. But while I'm executing that query, if someone during the execution of that query, right? Let's say I started at T0. Let's say someone inserted and committed something at T5, right? It's committed. While I'm reading it, I should not see T5. I only looking for T0s, right? That's the definition of read committed here. If you think about it this way, then you can definitely, in that particular, say you're isolated, but the next query that you execute, even if it's the same, it's not going to be the same, right? So make it another little bit simpler. If I actually do the select statement on one value, let's say I'm looking for a particular unique identifier, I'm reading a row, I'm reading a column on a row where ID equals 7, right? That 7 value, right? If someone, while I'm reading it, someone updated a value, I will not see it while I'm reading it. But the moment that other transaction commits, let's say it changes an attribute in that, and then the next query, I read the row 7 again, I will see that change because I'm read committed, right? Although my next query, right, the reason is the next query I did started at a different moment. So I need to see everything right before that's the query started. So that's read committed. It works. It's beautiful. It's simple. It just works for everything. So someone decided, okay, let's just solve that problem, which is the non-repeatability of the same thing. I read a row. I read something. I read a row. Now I read it again, and you're telling me it's different. I don't like that. Especially if you're generating a report, all of a sudden you're reading a value and then that product price has changed, right? You don't want that in transaction, right? And if I'm in a transaction, I want the reads to be repeatable for the row that I read. Very critical that statement I just mentioned. Let me say it again because I say it too easily. For the rows that I read in my transaction, make sure that they are repeatable. That is the definition of repeatable read. Repeatable read only guarantees that the things that you read will remain the same. So if go back to our row 7 example, if I start to begin a repeatable read transaction, isolation level, I read row 7, and after that, someone changed row 7 to some other value, other attribute. I read it again, guess what? I don't see that change. I see the original change. Let's say someone deleted that row. I read it again. I see the row. It's not deleted for me. As long as I'm reading it, right, the row will never change because the repeatable read obtains a lock, a special lock on that, such that, hey, I want just for the rows just for the rows I read to remain the same. What is the problem now? The problem is for range queries. You said, Hussein, that the rows I read. So let's do a range query. Give me all the students who scored grades from 90 to 100, right? Give me all those students. And let's do it in the repeatable read. So I do the first query. Give me all the students from that scored 90 to 100. Let's say we got 10 students, right? Student 1 to 10. Like they are ordered for some reason, right? And then I execute the same query again. But before I execute it, someone inserted a new student with a new grade. Let's say the 97. They got a 97. Though this is a student 20, right? I inserted that. I execute the query again. Does the 20 comes back to me? Do I get that extra one? And the answer is yes. In repeatable read, that is the theory. I'm talking about the theory now here, right? The theory says that the next read will do the same range query, will get that 10 students, remember, and it will make sure those 10 students don't change, right? Because we acquire a lock on all of them, right? We made sure that those guys will not change. But guess what? We never said anything about new things. That new 20 will be picked up, right? Because we never acquired a lock on that guy. It's a new thing. It's a phantom row. Phantom reads are picked up by repeatable reads. And that is the problem with repeatable read, right? I'm going to mention Postgres in a minute. This doesn't happen in Postgres. And this is where implementation is a different story than theory. We're talking about theory. We can theorize. We can say this is how you implement it. In my opinion, computer science should never say how things should be implemented. Just tell us what it is. Just tell us what this thing, and the implementation should just be left to the implementers. Don't say, oh, use locks. And that's the problem. The repeatable read. People say, let's use locks. It's like, no. Postgres says, no, I don't want to do that. Why? They broke the rules. And there are no rules. Why should I follow rules? My goal is performance. Why? And that's what Postgres did. We'll come to that point. But now that we explained the repeatable read in theory, they invented a new isolation level to fix that problem. In my opinion, snapshot should never existed. Or let's say repeatable read should never existed. Just call it snapshot. Just call it something one thing that solves both problems. That solves this repeatable read and the phantom thing that happened in the moment. The snapshot isolation, what it does, the query, the read moment start at the transaction level. But every single row is labeled with a version, is labeled with a timestamp, whatever you would like it to do. Okay? If you do that, so the way people define snapshot is really confusing because the moment you say, oh, it's as if someone is reading a snapshot. If you try the transaction, you read a snapshot of the database. The first thing that comes to the student mind, oh my God, are we taking a snapshot of the whole database? No. The problem is that nobody clarifies that. It's a bad idea to take a snapshot of the transaction. What? That doesn't make sense. Start a transaction and take a whole copy and then read on the copy. That will never scale. But that's the problem, right? We don't articulate things clearly. right? So in the snapshot isolation level, while the word snapshot is so confusing because I am actually a snapshot to us implementers is you're taking a snapshot of the whole memory or the whole database, actually a snapshot. But no, it looks like a snapshot. Please implement it as if we're doing a snapshot, as if someone copy the database and start reading that snapshot. So they are completely isolated. That is the complete isolation level. Don't let anyone read anything else, right? Someone changes, I don't care. So now comes to the implementation. How is it implemented? Every single row is labeled. You insert a row, it's labeled. You insert it at T7, or it is, if it's timestamp, you can implement it with versions. That's what Postgres does. It's versioned. Every transaction has a number, and that number is, you can think of it as like a version. Like transaction 1 is version 1, transaction 7 is version 7, right? So the higher transaction, the newer the row. Right? So if I create a row in Postgres, let's say I'm transaction number 1, that ID is saved in the row as a value called xmin, right? And the snapshot isolation, how it works, says, hey, when I start a transaction, that is your read moment. You read only at that moment. That's what you do. That's why people love Postgres, because this is so simple. They said, we're not going to do all this. Everything is read uncommitted. I don't want it. Remove it. Read, repeatable read. Yeah, it is the same as snapshot. We're just doing the same thing, right? Everything is labeled. Everything is versioned. And when I start a transaction as a snapshot isolation, right, I start at T0. Now, if I query, range, not range, who cares? I'm going to get a set of rows. I'm only seeing rows that are created before or at T0. If someone inserted a new row at T1, I don't see it. Even if I see it again. Why? Because I read at T0 and older. I don't care about new stuff. How simple is this? That's what repeatable read, in my opinion, should have been. Just make it repeatable. Okay? And the idea of phantom will never exist. Who wants phantom, right? That's what's I call like overcomplication, and when it comes to theory, right? I don't know. Maybe I'm making things up, but I come from a practical, I have over 20 years of experience working with databases. And if you build application, you're getting into the weed. You're building things. Right? You don't need to sit down and theorize on how things will look like. And, what if this, what if this? The problem you have, solve it. Right? And that's a mistake I made in this course. I focused very much on these phantom reads and things like that instead of actually focusing on the practical side. I changed that later in the course, as you might seem, but yeah, Postgres. What does Postgres do? What does Postgres do? Postgres have implemented one way. They say, why would I have like 7 implementation? Why do you want me to do locks for repeatable and then for snapshot use a version? In real life, nobody is gonna do that. Nobody. Why? Why do I have to do 10 different implementation? Like, make things simple. So whoever designed these isolation level never thought about the implementation. They say, okay, do this and do that. Make things simple. That's why Postgres is loved, because it's so simple. So this is what we are doing. I'm going to label everything as versioned. Transaction IDs, that's our version. Like, how simple is this? It's so simple. And as a result, sure, I'm breaking the rules of the isolation levels. Who cares, right? They are rules put by people, right? You can break anything. It just doesn't make sense. So repeatable read is snapshot isolation in Postgres. I haven't checked about other databases, but you will not be surprised that this rule will be broken, right? And that's why snapshot is not really even listed sometimes in things, right? Because it's just assumed that you want snapshot. Right? Now serialization is a different story, right? Serialization can happen. The problem with serialization can happen even in a snapshot because of the way we implemented things, right? The serialization happens. The problem with serialization is the problem with snapshot, I suppose, that still happen is when you read something right? When you read two values, like a transaction 1 reads two values and transaction 2 read two values, and it makes decision based on those two values, and later these two guys change their own value, right? So you read something, but you wrote to something else, right? So the two transactions actually didn't change the same row. They changed completely different rows, but they read each other's value before. And if you read something, you're going to make a decision based on what you read, right? And if you do that, then the order in which you write really matter. Let's take an example, right? For serialization and end this lecture. The best example I can think of is the hospital example, right? Let's just go back to face only, right? So the best example I can think of is really the hospital example, right? Where let's say you have two doctors that are on a shift, right? The rule in the application, right? And then, again, I'm saying the application, have nothing to do with the database. Right? At the application rule, the hospital should have at least one doctor on shift. You should never have zero doctors because you need people to get treated, right? So if a doctor, let's say two doctors are on shift, right? So you have a table called doctor and they are on shift, right? So if you want to sign out as a doctor, you cannot sign out if you're the only one there. There must be another doctor other than you that is on shift right now in order to sign out and leave, right? So let's say I am Adam and Bob. Adam and Bob are both doctors. They start the transaction and say, okay, I'm gonna read. Is there another doctor? Adam reads. He says, oh, Bob is there. So good, I can sign out. I'm going to mark myself as inactive anymore. I'm going to remove myself. I will just update the statement, update my row, my Adam row to not available. I'm not available. So update my row. Bob does the same thing. He queries. He says, oh, am I the only one? Oh, Adam is there. I'm going to mark my row as not available. So they both touch different rows. So there are no conflict on rows here, right? You're not really changing something else. Nobody is writing the same row. They're writing different rows, but they did read the same rows. They did read the same table. So in this particular case, you want those transactions serialized because in this particular case, here's an example where this snapshot breaks it, right? And even all isolations actually breaks it except the serializable, right? In this case, let's start with read committed. Read committed. Both guys start at the same time. They both try to sign out, right? They both start the transaction to sign out. Start transaction, right? Adam reads and he says, okay, Bob is actually there. So I can actually safely sign out. So Adam goes and changes its own row, right? And says, I'm not available. But before it commits, Bob does the same thing. It does a query, right? And says, wait, let me check. It's like, is there another doctor? We read, because we read committed stuff. Guess what? Adam didn't commit yet. So what do I going to read? I'm going to read the value that is actually available. So Bob thinks that Adam is available, but he's not because of concurrency reasons. We have race conditions. This can easily happen, right? In a concurrent system. Now we read the value that, Adam's available. I'm going to sign out. So both of them, then Adam, right after they read the value, what happened is Adam commits that, I'm not available. Bob commits, I'm not available. Guess what happened to the hospital? Nobody's there because the system allowed it. The system should have failed, right? But the check has missed because of concurrency reason, right? Let's try repeatable read. Same thing. We're going to start the read. We read the state. We read something that is not committed yet, right? So, we read something before it was committed. So still, repeatable read, same problem. Snapshot isolation, same problem. Because you're still reading at the old moment, right? So, of course, you're not going to... Actually, snapshot and repeatable read is actually worse if you think about it, right? Because snapshot... Snapshot and repeatability for that matter, they will, Adam may commit, but even if Adam commits, Bob will not see that change because they are reading the start of the transaction, right? So snapshot is really bad when it comes to these race conditions, right? So the best thing is, close to thing is the read committed, right? But even read committed, you can get this problem. So how do we solve it? One solution, forget about isolation level. Let's serialize. Physically, pessimistically serialize, right? We know this stuff, guys. We know how we build our databases. When I read something, I'm gonna lock I'm gonna do a select for update, right? I'm gonna do select for update, both, the whole table, anything that I read. If I read Adam, I'm gonna select for updated, right? And Adam will do a select for update and the same thing, and they will be blocked because guess what? Someone must have read it first. That's how I would like to do it. I like this approach. You can disagree, right? Theory, I don't care about this stuff, right? That's how real systems are built. Pessimistically, let the other transaction wait. I'm fine with that. A lot of people disagree with me, but I like to wait. I rather wait and my transaction succeed or give me a result than do an optimistic approach so that, let them all throw it, and at the end of the day, after 5 minutes, I was like, you have to retry the transaction because blah, 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 blah. I don't like that. It's just me. I don't like optimistic concurrency control. I like pessimistic concurrency control. When I do a select for update, just wait. So select for update can solve this problem. If you would like to go the optimistic way, which you can use a serializable isolation level, it will detect this for you, right? It will say, by the way, you read something that other transaction also read. The moment two transactions read the same row, right? And you read something that I changed, or this transaction read something that has changed, that is a serialization failure. It will detect, something has changed. You read something that has changed. You might have read something and that is now out of date. And the serialization isolation level will tell you, hey, there is a serialization failure. It will say, retry the transaction. So serialization technically is an optimistic concurrency control, right? Because it detects these race conditions. You can do this way. I prefer to be in control. I in my career, I never used actual serializable isolation level. If I can control it myself, this heartbeat of the pessimistic concurrency control to obtain a physical lock, that solves the problem. Why need a new thing? So I personally didn't see a use for serializable isolation level that beats the pessimistic. Now you can come to the conclusion that says, okay, wait conditions. Like, what if you have a lot of concurrency? Like, I know this lecture is long, but I think you got a value out of it because we talked about so many things, right? And in general, what happens is the weights and blocks are a real problem, and this indeed can happen, and deadlocks can happen as a result of the implementation that I told you about, the select for update. You can definitely get into deadlock. You can definitely get into weights, right? But how often are the deadlocks? Not often, right? But they can happen. One of the transaction will die anyway, and we're gonna retry. But in the serialization, every time that serialize happen, you're gonna get an error. So you have to have the application retry, right? The chances of deadlock are so rare compared to chances of serialization errors obtained by the serialization isolation. Again, don't let my opinion force you. You understand the fundamentals. You make your own decision. Understand the difference between the two. You get to make the choice as an application developer. None other than you can make that choice, right? But that blocking is a problem, right? That's another thing. If I acquire a lock, the other transaction has wait. It's like how long it waits it depends on how you built it, right? Like that's where you have to think. Like, when is it safe to commit? How long I should wait, right? And if you understand how database works, this is not a problem, because I know that the wait is gonna be a few milliseconds, right? And the doctor will just immediately commit. It's not like we're doing a huge huge transaction updating 700,000 rows and then committing, that the lock will be held for the entire transaction, and that takes time. So careful with the type of queries. If the queries have order bys, that's going to be slower, right? Always think about all these things. And I hope that I explained all type of isolation levels here in this in this lecture. It's kind of started with a question, but turns out to be a lecture for all isolation levels in details. Hope you enjoy it. I'm gonna see you in the next one. Welcome to another Q&A lecture. Today we have a question from Peter. Peter asked, isolation, repeatable read versus snapshot. So the question is, right, so Peter is basically trying to understand and give us an example between repeatable read versus snapshot isolation, right? Again, isolation levels are, think of it as just a single instance. We're not talking about distributed or anything, because I got that question as well. It has nothing to do with distributed. It's just a single instance. That's where you're isolating the transactions. So we have, here's an example he pulled from the internet execution order. So we have select pit ID, pit name, score from pit show. It's a table called pit show, where score equal select max score from pit show. So he's getting it the pit ID who got the most score, whatever that means, right? That's what it's trying to do. So there is a inside in a query that is inside another query, effectively, and max will return always one value. So we want to find out which one is that. The way I would have written the query differently, right? I would just do an order by. It's like cheaper in that particular case, because these are two queries versus I'm going to do select pit name, score, order by, score descending, and then limit one. I'm going to fetch the first one. That's basically how I would do it. I don't know which one is faster, to be honest. Right. This is fast because max, we know exactly where the score is, assuming the score is indexed. And I know we're talking about data modeling here and performance, but I thought it was going to be useful. The score in this particular case, that if it's an index, this will be immediate because I know the last page in the index, go and fetch that, and that will give me the last score. So that's fast. And then this is a B3 index scan to find that value, which we just found, in order to find out the bit ID, the bit name, right? And the score of that score, right? So in this particular thing, we're going to find the score and then go jump back to the heap, get the bit ID and other columns, right? So two queries versus I'm just going to do a select one query, order by score. And in this particular sense, since the order by is index, I'm going to go to the, I'm just going to walk the index in a reverse order. No, it's actually faster to do an order by. Yeah, because I'm gonna go to the last one and find the last entry and immediately jump to that, right? So it's one query versus two, if that makes sense, right? Yeah, definitely it's faster to do a select, but it doesn't matter, right? It's not that question. So we have one transaction that does this, select a query, select max score of someone, and there is a query one where we have updates the score, and when you update the score, obviously this might change, right? And that's what he's asking. It's like, if I am in my transaction and I query this twice, right? And meanwhile, I first query get a pet ID, and then someone updates the score and commits, and then I query it again, right? And what is the behavior in repeatable read versus snapshot, right? So if you do a repeatable read, if your TX1 is a repeatable read, what will happen is you can execute the query, someone will commit something, change the score, so the pit ID will change, and you're going to execute it again, right? If your query is repeatable, if the transaction one is actually isolation, is a repeatable read, then what will happen, unfortunately, is you're gonna get different result. You might say, what? I thought repeatable read will give you a repeatable read. Well, repeatable read will give you a repeatable read for things that you actually physically read, a row that you read, right? If you read a row and that row has changed, reading that same row will give you the same value. But that's not the case here. What changed here is something completely different. No rows were changed. Rows were added, right? And when rows are added, the nature of the query is now, because of the repeatable read is read committed, it's gonna see the new stuff. This is a side effect of something called phantom read, which we talked about, right? Because we're inserting things, my query is now detecting those new things all of a sudden, right? Phantom reads cannot be solved by repeatable read isolation level. Even that statement is not true anymore, because databases break the rules all the time. It's not that the rules are great, but they break it for a reason, for performance reasons, right? And correctness. So in this particular thing, repeatable read will give you different results, right? Because you are technically not reading the same row. You're reading a different row, because now your select score, max score, will give you a different result, because there is a new score right now. We just added a new score. So you're going to get that score, and as a result, you're going to get the pit ID for the new score. So repeatable read will not solve it. A snapshot will definitely solve it. Snapshot will give you a version. Say, hey, I don't care. I started this transaction. My current version or timestamp is T7. Please read anything T7 or older. Never read anything T7 or never read T8 or T10 or T9. I don't care. So if those things are committed in T10, I'll never see them, because I filtered. My snapshot isolation is filtering based on a version, based on a timestamp. And that's very powerful, right? And that's how basically Postgres works. Postgres doesn't have a concept of snapshot isolation, because repeatable read is a snapshot isolation. Yeah, I just contradicted myself. Right? The way Postgres implemented repeatable read is as a snapshot isolation level, because Postgres only have versioning. Because I would talk about the idea of version, right? Every time you touch a row, a new version is created for that row. So it's by default solves the phantom reads. As a result, Peter's problem is not a thing here in Postgres. And I'm not sure in MySQL. It might be the same. Can be quickly verified. Just spin up a MySQL instance on a Docker container and try it out. It should do a max in another transaction, update the score, and then in the same transaction, obviously begin the transaction, and then do a max, and then update the score, and then do a max again. You can, if you got the same thing in a repeatable read, that means repeatable read is implemented as a snapshot isolation level. Hope you enjoyed this lecture. I'm gonna see you in the next one. You guys stay awesome. Goodbye. Welcome to another lecture in this Q&A section of the Database Engineering Fundamentals. And today we have a question from Kirati. Sorry if I didn't pronounce your name correctly. It's a very good question, actually. It says, hey, I have a Postgres using sequential scan rather than index-only scan. Why is that? And that's a very good question. Let's take a look at what was Kirati's question here. I'm using PostgreSQL. I have created a table with 4 columns: ID, first name, last name, date of birth, and I created an index on the ID field, which is a primary key as well. When I do a select query like this, which is a select ID where from, obviously he forgot to add the table here, select ID from blah blah the table where ID equal to, he is getting it is using a sequential scan rather than an index only scan. What's the issue here? The table has only 7 rows. Even if he didn't say that, I would have guessed that his table is small. Right, so my guess is here. So what is happening here? Right, so I already answered here, but I'll give you a hint of what's happening here. You see, Postgres or any database planner we're gonna understand how things work, right? We have the data of the table in a file, right? And we created also an index, which is another file. And the index has the structure of, we talked about the B-tree structure for an entire section. It's a complex structure with so many intricacies, right? Where we have a root, we have intermediate nodes, we have this, we have that, we have leaf nodes. We have complex structure here. And we have the data file, which is just a dump of everything that is in the table. So when we load the database and we start querying the table, what the database will look is like, okay, we have the data file and it's a single page. Why is it a single page? Because it has only 7 rows, and the 7 rows happen to fit neatly inside that page. A page is around what, 8K in Postgres, I think. So this is way too small of a table, right? So it's a single page. And here's what the database says. All right, what I'm gonna do is actually, yes, you start using the ID field, but guess what? It's not even worth it for me to go to the index, because to go to the index, I have to do 2 things. I have to go to the index, I have to fetch the index, I have to build the B-tree index in my memory, and then I have to traverse it just to find everything that has ID equal to. Versus I know the whole table is in 1 page, and that will cost me 1 IO. So here it is. I'm going to do an IO, and I'm going to pull it in memory, and that goes to the heap, as we talked about it, the Postgres heap. And then that page in the heap was there. All right, here it is, user. Because we just read all the things that are ID equal to, and it's a single read. It's a sequential scan in this case. That's why tables, right, in this particular case, that are too tiny, the database will just do a sequential scan on the heap, right? It will just fetch 1 page, and that's 0 cost almost to Postgres. Right? Now, here's where it gets interesting, and I've got bitten many times that I have count with this actually. And here, so I have a tiny table, and I start querying this like what Kirati did here, right? I was querying it, and the plan started getting cached. It says, oh, this table is too tiny, so sequential scan is the best. I don't want to go to the complex B-tree and scan many indexes to get my results. I was going to do a sequential scan because it's just it's a simple table, it's a small table. And what I do is, immediately after doing all the queries, I would insert my data. And when I do that, right, what will happen is I start like inserting 3 million rows, right? And immediately after 3 million, I didn't give the database chance to breathe. I would start querying, right, for a few minutes. And my queries are so slow. Why is that, right? Why are my queries slow? Because the database thinks the table is small. So if I issue a query, the statistics, and we talked about statistics in the course, the statistics which tells the table how many rows are in there are not up to date with the 3 million rows that I inserted. So the planner thinks, oh, it's a table that is small. Let me go and query it. And when it does that, it says, uh-oh. It starts doing a sequential scan of an actual, instead of an actual performant B-tree scan. Because remember, B-tree scans or the index scans are very amazing when you have large amount of data, because you're going to traverse few blocks, but then you're going to find exactly what you want in the B-tree. Immediately go to that, right? That's the problem here. The problem is the planner is out of date, right? The cache, the stats are out of date. So the planner thinks, let me do a sequential scan. So it starts scanning the entire heap, fetching millions of pages. I'm exaggerating, thousands of pages to find what I'm looking for. Why? Because it was out of date. Obviously, this is a very common problem when you just insert the data and immediately you queried it. That's something you have to watch out for. That's why after inserting a lot of data, you have to do a vacuum in case of Postgres, and in case of Oracle, you have to do a vacuum analyze, I suppose. We'll do a computing the stats again. It will just do a count again, says, okay, this is how many active rows are there. I'm gonna update my stats so the planner will make smarter decisions. And in Oracle, I think it's called gather schema stats, and in SQL Server it's called something else. And that's updating the schema stats are very, very critical in this particular case. So this, I thought it was a very good question, and I thought I'll talk about it here because it's really something you have to watch out for. And very good observation, Karate. I like that you guys are actually looking at the plans. It says, wait a minute, I'm using an index. Why is it not using the index? It's a very smart thing, right? Even with an index only scan, it's not fast enough, right, to fetch the index compared to just having the one page, right? If you add a few rows to your table, more few rows, that's 10,000 rows, you'll immediately feel. Hope you guys enjoyed this Q&A lecture. Okay, see you in the next one. Goodbye. Welcome to another Q&A section for the Fundamentals of Database Engineering course. Today we have a question from Shivana Show. Fetching a page versus a row in an index. Right? Hi, in lecture 16, where you explain how indexes and tables are stored, you mentioned that when we execute a SQL query behind the scenes, the whole page is fetched, and only the row needed is filtered and sent to the user. That is correct. I have two questions. Why does it get the whole page? Why not the row, since the DB already knows the row location? That is actually not a correct statement. The database does not know where the row is in the database, in the page. It has to read it. I'm going to explain why. Right? The database knows that the row is in the page, but it doesn't know exactly where in the index. I'm going to explain that why. Okay? All right, let's just explain and then go to the second question. So why is the database doesn't really know where the row exactly is? Because let's say the page is stored on disk, that's what it is, right? The rows are stored in row store, right? So that means the row, column 1, column 2, column 3, column 4, column 5. And then the second row immediately comes after that. Column 1, column 2, column 3, column 1, column 3. So the rows are just one after the other. So your statement, right, Shivana Show, is correct. Hope I'm pronouncing your name right. Your statement is correct if the row size is fixed, which is pretty much, I never seen it anymore. The only time the row size is fixed is in a MySQL database engine called MyISAM. And that's pretty much it. The row size is never fixed. It's variable because you're going to have a string that is long. Some columns will have a shorter values. Some columns will be nulled. Some columns will have values. Some columns will have a blob. So some rows will be fat. Some rows will be thin. Even the column, even if the number of columns are fixed, right? The row sizes are never fixed. You might say, why not? Why not always have them fixed? That's what my ISAM did. But we quickly found that we're wasting a lot of space, right? Because if a string is empty, like let's say if a string field is like 255, it's really wasteful to put 255 blank spaces if there is a null in there, right? Because that's the only way you're going to make it fixed, right? If the row size is fixed, then we don't have a problem. But unfortunately today we have unfixed row size. That means the number of rows in a page are not fixed either, because you can have a row that is so big that a single page will have a single row because it's so big. Or that's why you have a limit in number of columns in databases. You can't just put unlimited number of columns because there is a fixed page size and the rows inside it has to fit inside the page. There is another thing, the database constraint. You cannot just have a row so long with so many columns that is starts spanning multiple pages, it becomes very problematic for databases. So databases put constraints. Hey, you know what? Fixed page size, rows can't span pages. Okay? So when you start understanding this thing and you store this page in disk, you know where the page is, sure, because it's a fixed page, right? So you know page 7 is in this position in the data file. Go there and pull page 7, sure. And that will be transmitted into the file system blocks, and in the SSD will be transferred from logical block addressing to the physical block addressing, and NVMe will take care of from there, right? And then we will fetch exactly that page. But the row, nope, they don't know, right? We don't know exactly where. Even if you did know where exactly that row is, there is no concept in hard drives that is called byte addressability. You cannot just go and fetch 1 byte or 3 bytes. You have to fetch a block, right? And in disk space, this is, I think, 4 kilobytes. It depends on the SSD. So you have to fetch a block of data. That's the limitation we have today with hard drives and SSDs. You gotta fetch a page, right? And I'm very sorry, page and block is a very overloaded terms. So I know I'm using them interchangeably. That's how the entire industry uses them. Nobody can agree on anything. So you gotta have to deal with that. Right, but when I say page, I mean databases. When I say block, I mean disk, physical spaces. And people use the word sector here. Nobody can agree on anything anymore, fortunately. But this is where it is. So when I do that, a page will consist of multiple blocks, file system blocks, which will transfer to an actual hard disk block. That's what makes this very hard and confusing to talk through, right? When it comes to pages and blocks and stuff like that. But yeah, so we don't have like the RAM where I can go and fetch that byte, that particular row and nothing else. I don't want to go over the whole page. Right? So your question is actually valid. You're challenging the database system today. Maybe you're going to come up with a database that actually solves this problem. Today we have a problem. We fetch a page that has so much stuff that we don't need. I just need the row. Why are you giving me the whole page? So there is a cost of fetching, reading IO from disk. There is a cost of transmitting. There is a cost of parsing at the database level. I mean, transmitting, we don't really transmit stuff we don't really need unless the client is asking for stuff that it doesn't really need, and you end up transmitting it in the network. So that's basically it. So in the RAM, you have byte addressability, so you can actually do this trick. Say, hey, go to that address, give me that byte. There are other systems that tries to do a disk, an SSD that is actually byte addressable, which will allow us, if we know where the actual row is, to go to that file and fetch exactly how much we need. That is going to be so powerful in that particular case. So what we end up doing is we try to be clever and says, okay, when I fetch a page, I'm going to make sure that all the stuff that I need is in that page. That's where clustering comes in and the concept of primary index here, right? So I hope that makes sense, because we talked about most of these concepts in this course. All right. How does this work during the index? I mean, in an index points you exactly to the row. All right, so here's another good point, right? So he's right. The index, when I traverse the index, I find the index and I find exactly the page and the row ID. It's not a row index or position. It gives you the row ID. It's an identifier. It's not a pointer. It's not an index in an array. Don't think it's an ID. It's a tuple ID. So when I get that ID, I'm responsible to go to the page where this ID lives. And again, I'm going to fetch that page from the heap, where the heap was populated from the disk, right? When we read a page, right, from the disk, we put it in the heap. And in the B tree, when we scan the B tree, what is the B tree? It's a bunch of files. Right? It was at some point, it was something that stored in the file, and we fetched it from the disk, put it in memory, and then we built pages out of it. So even when you read the B tree, you're reading pages, right? The root is in a page. These intermediate nodes are in a page. So you happen to read one node, maybe one page happened to have 3 nodes, right? I believe the B tree structure is one page equal one node. That's the de facto, right? So when you read one page, you get one node, and that node have n elements in it effectively, and we talked about that in the B tree, right? But once we find the root and then find the row, right, the row will live with many other stuff in a page, right, in the B tree leaf page, and you're gonna have a lot of them, a lot of rows, because you happen to read that leaf page, and the leaf page will have many entries, row IDs, and then you have the row ID. Now you have to go to the actual heap, which will have the row ID and all the columns, because remember, the index only have one or whatever columns that you actually indexed. In this case, you go back to the heap, fetch that, find where the row ID. You have to find it. You cannot, unfortunately, go to the, it's not an indexed position, right? So you have to read all the rows in the page and find out exactly which one is yours, right? And you can't assume order either, right? You have to keep looking until you find things in the heap. The heap is not ordered unless the whole thing is clustered. That's a different story. So I hope that clarified it. But that's a fantastic question. I like question like this, because it sounds like students are actually challenging what is existing today, and this is exactly what I want. I want you to not take anything for granted here. I'm not teaching you per se. I'm just showing you the wave. Does that make sense? I'm showing you how things are today, and you feel free to challenge anything, because nothing is perfect. Hope you enjoy this lecture. I'm going to see you in the next one. Goodbye. Welcome to another Q&A lecture. This is for the month of May 2022, and the question for today's lecture comes from Robin. And if you don't know, guys, this is our series in this Udemy course where we pick one of your questions, fantastic questions. All of the questions I get is amazing, and I try to answer all of them to my best of the knowledge and obviously time. But for those questions that need some more time, I dedicate a lecture, like this. So this comes from Robin Srivasta. Let's read it and discuss. Index on column with duplicate values. I absolutely love that when you guys watch my lectures and then start thinking about these cases, because they are real world cases. Right? I never mentioned anything about duplicate values, but this comes to you, right? As you think about it. So let's talk about it. And this is how you basically, you see yourself evolve, right? As you ask these questions, that means you're penetrating and you're breaking these walls, the confusion and everything, right? So let's read the question. If you are creating an index on column which can have duplicate values, so it's a non-unique index, right? Then how is it stored in the index data structure? Does it maintain a key with a name as duplicate values, a list of rows, or corresponding page information? Here's what I want you to think. So this is for Robin and everyone here, really. Right? So question, I don't think we need this screen anymore, so let's go back to this and just talk through. And excuse my hair. I need a haircut. So the moment you find yourself thinking about how is it implemented, don't worry too much about that. What does that mean? It means that if you find a way yourself, like, don't worry about how big companies do it. It's like everyone makes mistakes. Everyone implements something and then finds out that it's not really efficient, right? So
You provided ways here to solve this problem. Work it out yourself. If you think these are optimized and they are fine, this is an implementation. There is no wrong and right. Yeah, there is one implementation that could lead to wrong results, and that's obviously not applicable, but there's implementation that is more efficient than the other. So that being said, I don't want you guys to worry about much. It's like, oh, if Postgres do it this way, this is the right way. If MySQL this is the right way. No, not at all. From my 20 years of experience, what I have been seeing is always I've been worrying about, oh, if someone else implemented something that must be better than my idea. No. As you gain more experience, of course, if you're new to the course, you're going to stumble upon things that you've never seen before. You might have ideas, but they might be shut down because you still don't have exploded knowledge. But the more knowledge you get, the more confident you become about your implementation. I think I got on the tangent, but I think it's a little bit valuable here to talk about. But so the index duplicate value. So let's start with this. If you have a column, right? I don't know, gender, right? What are the values in the gender column? Right? Male, female, unspecified. You don't want it to specified, or you can have a little bit of a spectrum there based on what you want the data model to be. But let's say you have 3 values. Right? The moment you have these 3 values, right? If you have 100 million rows, indexing that column becomes useless. Like, think about it, right? Adding an index on that becomes really, if you're just searching for, all the, male who watches their certain shows, right? For example, or females who watches this certain show, like, building a system, something, right? To gain experience. Indexing that column, just that, becomes really useless because, remember, there's something called index selectivity. So index selectivity means you want the index to give you as small a result as possible. So if you index this and like 99% of the value is the same, then it's pointless, right? Because it didn't reduce your result set. It's not selective enough. And that's something to worry about. So that's one thing to have worry about. But sometimes there's duplicate values regardless, right? But there's like more selectivity. Like, so there's a bunch of duplicate values, like say categories, like a movie show category, right? Then that has more variety, right? So the values becomes duplicated, sure, but they won't be as dense as like if you have 2 or 3 distinct values. Does that make sense? That being said, you can combine that index with other things to make it more selective. Right? If you have other indexes by itself, that's what I mean by itself. It would be useless if you have a lot of duplicate values with very small distinct values. So the solution here. Now I'm going to answer Robert's question again. I felt that whatever I said is like kind of relevant to this. That's why I mentioned it. So to have duplicate values, let's say I'm indexing column, and let's think about something like, product code, right? And you have like 10 codes, right? So different products will have the same codes, obviously, right? It's like, this is not unique. This is like a code as a category, I mean. Right? So code 0, code 1, code 3, code 4, up to code 10. So let's say we have 10 products with the same code 0. So if you index product code, then how does the index looks like? Without being smart. How do we do it today in the B3 leaf, right? Again, you have to watch the B3 lectures to understand this. But what we're going to do is the key becomes the code, right? So code 0. And then the value becomes the row. right? So let's say row 1. Depends this is a primary key or a secondary key. The value will be either a pointer to the primary key, so there will be a primary key of the row, or it'll be a pointer to the row itself, if it's like in case of Postgres, right? If it's a secondary key. Or if it's a primary key that you're looking at now primary key cannot be unique, so forget about that. So yeah, so it would be the code and the row itself, right? The row ID, which is like 32 bits. It depends on the size of the row. And yeah, if it's primary key, then it's going to be like the key, primary key. That's why you have to be careful. What is your primary key here? Because it will be duplicated, right? In this case. So code 0 becomes this, right? This value, row 1, right? Let's say. And then code 0 again is row 2. And code 0 is row 3. And code 0 is row 4. And code 0 is row 5. And code 0. So that's how we're going to do it. Right? Obviously, if you think about it, you just duplicated the value 0 many times. So if you're indexing a 32-bit integer, that's 32 bits, 32 bit, 32 bit, 32 bit in the index. So the index will be bloated, right? So that's what we have today, right? As a naive implementation, if you will. Only, right? This was implemented for the longest time. It's only recently when Postgres, I think Postgres 13 implemented something called the deduplication in the B3 index. So that what they did is they deduplicated this. So that in case of doing 0, row 1, 0, row 2, 0, row 3, they would put 0 and then a specific array of all the rows effectively that points to that, right? Or based on what Robin suggests, okay, let's put just the page information, right? That's what he suggested, right? Let's just put the page information, and then we can filter that when we go to the page, right? That's another implementation. So you can do any implementation as long as it, as you work it out and then kind of measure the value here. It really depends. But all comes back to what the user wants, what the DBA actually doing. Why are you indexing value? So if you're indexing something with a lot of duplicates, really think about it really hard. What value does this give you? Test it, do the explain. We've done thousands, of these lectures. Thousands. I'm exaggerating a little bit. But we did a lot, right? Talking about this. Always test, add an index, see, does the explain give you a better access path, right? It's all, at the end of the day, trial and error, thinking about, okay, yeah, well, the theory is sound, my use case might not be, might not fit this case. And that's basically what I'm going to leave it at. Hope you enjoyed this lecture. I'm going to see you on the next one. Enjoy the course.